Astronomers have been paying close attention to the interstellar comet known as 3I/Atlas after observations revealed behavior that sharply contradicts what is normally expected from cometary physics. At the center of this discussion is a striking feature, a jet-like structure associated with the comet's anti-tail that appears to be directed toward the sun rather than away from it. In typical comets, solar radiation pressure and the solar wind force dust and gas outward, forming tails that always point roughly away from the sun. In the case of 3I/Atlas, however, astronomers observed an extension of material growing sunward after the comet passed perihelion, its closest approach to the sun. This anti-tail expanded over a period of roughly 2 months and reached lengths of several 100,000 kilometers, making it both unusually persistent and unusually oriented. The sheer scale and direction of this structure have raised fundamental questions about how dust and gas behave in this object, and whether conventional comet models are sufficient to explain what is being seen. Under normal circumstances, a comet's activity is driven by sublimation. As a comet approaches the sun, increasing heat causes volatile ices within its nucleus to transition directly from solid to gas. This outgassing produces jets that carry dust particles away from the nucleus, forming the familiar coma and tail. Dust particles, once released, are influenced by several forces, including the initial push from escaping gas and the pressure exerted by sunlight. Smaller grains can be strongly affected by radiation pressure and may be rapidly accelerated away from the sun, while larger grains move more slowly and follow more complex trajectories. In some geometries, especially when Earth's line of sight aligns with the comet's orbital plane, a structure known as an anti-tail can appear. This is largely a perspective effect, caused by dust particles that were released earlier and now lie along the comet's orbital path. Even in these cases, however, the underlying physics still points away from the sun, and the apparent sunward orientation is an illusion rather than a true reversal of flow. What makes 3I/Atlas unusual is that its anti-tail does not seem to be explained by perspective alone. Observations indicate that the material forming this structure genuinely extends in a sunward direction, suggesting that forces other than simple radiation pressure and orbital geometry may be at work. Researchers have therefore turned their attention to the differing behaviors of dust and gas in space. Dust particles, once decoupled from the gas that initially propelled them, can travel great distances and persist for long periods. Over time, they may slow under the influence of radiation pressure and gravity, creating extended features that remain visible even when gas emissions fade. This helps explain how a jet-like feature can grow very large without strong, easily detectable gas signatures close to the nucleus. Dust follows its own dynamics, and under certain conditions, it can form structures that appear counterintuitive when compared to classic comet tails. Gas, however, behaves differently. Once released from the nucleus, gas molecules are strongly influenced by the solar wind, a stream of charged particles flowing outward from the sun. This interaction tends to sweep ionized gas away from the sun, forming ion tails that are often straighter and more sharply defined than dust tails. In most natural comets, this process dominates the large-scale behavior of gas, making sunward-directed gas flows difficult to sustain over long distances. The standard picture assumes that the energy driving gas ejection comes from solar heating and the sublimation of volatile ices such as water, carbon monoxide, or carbon dioxide. Among these, carbon dioxide is often cited as a particularly effective driver of jets at relatively large distances from the sun because it sublimates more easily than water ice and can remain active farther out. The challenge posed by 3I/Atlas lies in whether this sublimation-driven mechanism can account for what has been observed. Data from the Hubble Space Telescope indicated the presence of gas at distances exceeding 5,000 kilometers from the comet's nucleus, a detail that immediately drew attention. Gas detected so far from the core suggests either unusually efficient transport mechanisms or ejection velocities higher than those typically associated with ordinary sublimation. If gas is truly present at such distances and contributes directly to the anti-tail, then the energy required to sustain this motion becomes a key question. Standard models predict that gas jets weaken rapidly with distance as the material disperses and interacts with the solar wind. Maintaining a coherent, sunward-directed structure over thousands of kilometers would therefore require conditions that push the limits of known cometary physics. This realization has shifted much of the discussion toward the speed and momentum of the expelled material. If dust alone were responsible, one might argue that early ejection combined with favorable geometry could explain the observations. However, the detection of gas complicates this interpretation. Gas molecules are lighter and more responsive to electromagnetic forces, making them less likely to linger in coherent structures unless continuously supplied or accelerated. This has led scientists to question whether the nucleus of 3I/Atlas possesses an unusual composition, perhaps rich in volatiles not commonly seen in solar system comets, or whether the structure of the nucleus allows for highly collimated jets that can direct material sunward under specific conditions. Adding another layer of controversy, astrophysicist Avi Loeb has suggested that the observed anti-tail could be consistent with a technological driver rather than a purely natural process. In this speculative scenario, the jet's apparent launch speed and sustained direction might resemble the output of an artificial thruster. Such a mechanism could, in principle, propel gas toward the sun on scales larger and more coherently than natural sublimation would allow. While this idea has captured public attention, it remains highly controversial within the scientific community. Most researchers emphasize that extraordinary claims require extraordinary evidence, and at present there is no direct proof that the behavior of 3I/Atlas is artificial in origin. Nonetheless, the fact that standard explanations struggle to account for all aspects of the observations means that the object continues to invite unconventional hypotheses. Regardless of whether one entertains technological explanations, the case of 3I/Atlas underscores the limitations of existing comet models when applied to interstellar objects. Unlike comets that formed within our solar system, interstellar comets originate around other stars and may carry compositions, structures, and thermal histories that differ significantly from what astronomers are used to studying. Their responses to solar heating, radiation pressure, and the solar wind may therefore reveal new physical regimes. The sunward-pointing anti-tail of 3I/Atlas highlights how dust and gas interactions can produce unexpected outcomes, especially when combined with high relative velocities and unfamiliar material properties. The continued interest in this comet is also driven by timing. Even after its closest approach to Earth on December 19th, the object remained observable and scientifically valuable. The persistence of its anti-tail after perihelion suggests that whatever mechanism drives this behavior does not shut off quickly, further challenging simple explanations. As additional data are collected, researchers are focusing on refining measurements of particle velocities, composition, and spatial distribution. Each new observation has the potential to tip the balance in the ongoing debate, either reinforcing natural explanations or deepening the mystery. In the coming years, 3I/Atlas is likely to serve as a reference point for studies of cometary behavior that fall outside established norms. Its anti-tail behavior highlights the need to broaden analytical frameworks to better account for complex interactions between dust, gas, and the solar environment. Whether the ultimate explanation lies in unusual but natural physics or in something more exotic, the object has already demonstrated how much remains to be learned about small bodies traveling between the stars. By challenging assumptions and forcing scientists to re-examine the fundamentals of comet activity, 3I/Atlas may ultimately influence how future interstellar visitors are interpreted, ensuring that its legacy extends well beyond its brief passage through our solar system.